How's everybody doing this afternoon? You ready for the best topic of the whole conference? Or are you just guys ready to go home and get a beer or something? Both at the same time. I wish we could do that. That'd be even better, right? Beer and AI. Well, what we're going to do this afternoon, my name is Steve Scarborough. We're going to be going over and discussing how to enable discover or defensive cyber operations with AI. We're going to start it off with kind of like a high-level discussion on what AI is, just so we can set the framework so everybody can discuss it in the same fashion, right, and understand some terminology. And then we're going to go into a little bit more in depth into some of the techniques and procedures and tools and kind of methodologies and a couple of use cases to kind of like set it for you and so you'll understand it. Who's using AI right now for anything? A couple of people. Who is doing Python or any type of data analytics? A couple of people. Who wants to do AI? Come on, everybody's supposed to raise their hand. Everybody wants to do AI, right? So we're going to kind of demystify a couple of things, get everybody on the same sheet of music, right? A little background on myself. Everybody calls me Scribs. That's my nickname. Coworkers, friends, colleagues, adversaries, all know me by that. I was in the Navy for 20 years. I was a communicator and a network technician doing red team, blue team, discovery type operations. Retired in 2010, joined my company Intelligenesis, and now I run our IG Labs, which is kind of like the skunkworks discovery stuff. We do AI and cybersecurity in the same space. So if I blow past something you want to throw a discussion up, throw a hand up, say, hey, Scribs, you want to stop and talk about that? If you can't tell already, I do talk a little fast. So stop me. I'll go back. We'll discuss it. I like interaction. So if there's something you want to know, go ahead and ask me. All right, so what is artificial intelligence? Artificial intelligence, right, is advanced computing, but to the fashion of, not just thinking about it like taking over and replacing humans or anything. It's using advanced computational algorithms to be able to automate and help us make decisions out of larger data sets. It's different from using like big data analytics or using platforms like SIEM platforms. You run a specific query and get back data and present it in a particular way. We're looking at how we can process the data in a much faster, much more complex fashion to derive deeper intel, right, from that information. And the way we use that intel, right, is different means, right, or different purposes. When I'm saying intel, I don't necessarily mean like foreign intelligence or network intelligence. I'm saying intelligence to be able to do something next, right? To be able to make a decision or help us do a decision. You'll also hear me talk quite a bit, and I might say it often, is like we're not, in this discussion, we're not talking about replacing operators or defensive cyber personnel with an AI bot that does things automatically, and you're not going to have a job in a couple of years, right? We look at it from our perspective as we're developing things. It's artificial intelligence augmentation to the analyst, to the operator, right? To help clear some of those things out of the way that drive you batty and take up your time and need to be not just automated, but things that a human might miss in large volumes of data. How many of you work SOC operations? A couple. How many of you are doing like analysis on really large-scale data and looking at a SIEM all day long or some sort of dashboard, right? That can become really monotonous. And depending on how you or how somebody else has configured that query to pull information, whether it's out of Splunk or out of Elk or something else, we can miss things from that. We can induce bias within that query into that and then miss portions of it, right? When we get into some of the use cases, you'll see what I'm talking about. Now, artificial intelligence is comprised of a couple other areas you might be hearing a lot about, right? Mainly machine learning. Does anybody have an idea what machine learning is without looking at the slide? Right? It's a subset of artificial intelligence in which we're using the machines to compute those or run the mathematical equations to be able to derive that intel. So to be able to get artificial intelligence, to get to the level of artificial intelligence, we have to run machine learning to be able to train models, to be able to detect things and flow it together so that we can get to that intel piece, right? It's a much higher level than just your normal big data analytics. We're not talking, again, about looking at a specific subset. We're looking at, or a subset of data. We're looking at how we can use those algorithms to look at, atomic level information, specifically in cyber operations, atomic level information about packet data or network data or a threat data or human data and the way they operate, or anything you want to look at, right? Being able to go beyond just top level features of a set of information, right? It's based on applied statistics, right? We use those models, but again, it's not statistics in itself, right? There's some nuances in there, but it helps us derive that information to be able to do those things, right? In the machine learning world, there's a couple sets, and we're going to get into it a little bit later on what kind of machine learning, what kind of algorithms we're using to be able to derive that information from it, and what type of algorithms we use will determine the output that we're getting and some of the other pieces we can get from it, gain from it. Right. The final level here, and it's not necessarily the final, but the last one we're going to talk about or really think about is deep learning. Has anybody ever used any deep learning algorithms before? In the back. Has everybody ever seen any deep learning algorithms being used? Everybody's seen deep learning algorithms being used if you're using Google, or if you're using Facebook, or you're using Instagram, or any of these other things that we use, and you're getting recommender systems, or you're getting some other piece of information provided back to you from your applications or your phones, or some other piece, right? It's taking, and it's a much deeper version of machine learning, right? Where we take things, if you look at things like facial recognition or NLP, natural language processing, all those other like things that don't have shapes or defined feature sets about them, we can use deep learning to be able to derive it. As opposed to machine learning, where we'll take data and we'll split it into testing and training sets, the deep learning piece does that iteratively over and over and over again, so it can continue to refine its training so they can better identify those pieces. Has anybody ever seen that Microsoft commercial where the guy's saying they've been on the side of the Tibetan mountain and they've been taking pictures of snow leopards, and now they can use AI to detect snow leopards on the side of the mountain, and he makes it sound really super simple, right? They get to that point, they had to take millions of pictures and then go through and let the algorithms first identify a shape. What does a shape of a leopard look like on the side of a mountain? And the most basic shape is going to be just a stick figure. It's going to look like your 4-year-old drew a cat, right? It's got a couple legs, it's got a line for back, it's got something that looks like a head. On the next pass, it will then start identifying things like, oh, there's a tail there. It's facing this kind of direction. So it starts adding dimensionality to the data that it's seeing and transforming it. And then as it repeats over and over again, it becomes building up and becoming more refined so that it can find the snow leopard on the side of the mountain, right? Or faces or cars or objects or whatever it might be, right? So being able to build that out and do it repeatedly so they can go through. One of the things that we have to do with machine learning and deep learning to be able to obtain artificial intelligence is train those models, and then in their training and their movement, right, of them identifying information or driving intel for us, we have to go back and monitor them and watch them and make sure that we're not having problems with it. And we'll discuss that data drift and model drift and some of those other pieces along with it. But it's a continuous process. How many of you have been in a meeting with your bosses and they're like, we need to get some AI in here stat? And they think it's going to be like a panacea. It's just going to solve their problem. They get some AI dust and sprinkle over it, and everything is going to be solved, right? It's a very long, very resource-intensive process. It can be, I don't want to say extraordinarily long, but it can be a long process. It can take time. It takes patience. There's a lot of failures in it before you get to the solution that you're looking for. So it's just a matter of all those pieces. That's where it's important to kind of understand the AI development life cycle, right? In this, it applies to machine learning and deep learning and AI as well. Let me go back here. It applies to all three of them, but it follows the same basic process. And it can also be mapped to the scientific process, because it really is AI, machine learning, and deep learning in itself is a science. right? We're looking at things. We're going to be deriving hypotheses about our problem. We're going to be going through. We're going to be gathering data. We have to understand things like sample sizes versus population sizes, and our training of those models, being able to apply those models in the appropriate way, right? So the first step, right, is the project design, and in this cycle, right, we're gonna sit down with the people who want to have the AI done, right, the machine learning or anything else. So a mission set. It might be you, and you're going to sit down with a data scientist, and you need to be able to articulate to them what it is exactly that you're looking for. And at times, that's going to be very difficult because in the data science world, right? Anybody a data scientist? One data scientist in the back. So we might brawl afterwards. I have to be careful what I say about data scientists, right? So in the data science world, if you boil it down to, there's 3 skill sets that a data scientist will have, and they'll usually be heavier on one of the 3 data sets, or one of the 3 skill sets. First is going to be a mathematician, which I am absolutely not a mathematician. I will never, ever claim to be a mathematician. There are very few people in this world love being mathematicians, but if a mathematician is around you, they will tell you that they're a mathematician. All right? You're supposed to laugh at the jokes. Right? The second one is going to be a computer scientist, right? The computer scientist is going to be even broken down even further, and they're going to be data engineers. They're going to be coders. They're going to be something that helps get the platform going and be stronger in that aspect. The mathematician is going to be really heavy in the algorithmic design, being able to use mathematical equations to find those pieces. And the third, and in my opinion, is probably one of the more important ones, that's the domain expert, right? The domain expertise about the information you're going after. It's very difficult to take a data scientist who has limited or no domain expertise in cyber, but has a ton of it in, say, healthcare or in medicine, right, and put them in and be able to have a complete understanding of what the cyber operator is asking of them. It doesn't mean that they can't do it, but the communications process it breaks down a little bit when that's occurring. Now, some things will fall out from it, but we're in this first stage. It's very important to sit down and the customer and the data scientist come to terms with what it is exactly they're looking for and how they're going to do it. And the customer, if you're doing it, right, if you're the customer and you're trying to do some of these things, being able to explain to them not how to do it, but what you're looking for, right? And you'll see in some of the use cases what we're talking about there, right? Where's your target data at? Where's it coming from? Everybody in here has probably looked at PCAP data, right? Everybody's PCAP data? Right. Everybody looks at NetFlow data? Somebody's really happy about PCAP data. That scares me sometimes. Right. NetFlow data, PCAP data, it could be email information. It could be whatever it might be in any type of data flow that you're going to get. But where is it? How fast is it coming? How much is it? Where do you store it at? What APIs are there to be able to pull from that data? How is the data scientist going to get it? The AI engineers, the ML engineer, the DL engineer, how are they going to get it? They will then start selecting models and ideas of what can go into there. We're going to start looking at feature sets. And this is something that we've heard a couple times when we're working with our partners. We start talking about features, and they're like, well, what is a feature? And we're like, oh, well, that's an IP address, or that's something about the object that we're looking at. And they're like, well, why don't you just call it like data point, or why don't you we're talking about it being a feature. And everybody has a feature. Objects have features. And so that's how data scientists and how we reference those types of things within the AI, ML, DL development process. How that then leads into do we clean the data? How are we getting that in? Do we need to transform it? Do we need to put it in some other shape to be able to do run the algorithms on it? In text identification, we do an OCR, say we're trying to train a model to do or recognize American Sign Language, right? And we take a picture of somebody doing a sign, and we have to take that. It's not actually looking at that picture. It's transforming the picture into a different object. And that object, the shortened version is that it takes every pixel in that image and it puts it into a string, and then it gives it a gradient of gray color, right? And then that becomes the way it judges every other piece. And over time, we can feed it the same image or the same shape or the same hand sign, and it will begin to see it in different ways and begin to be able to have a more tightly fit and more better trained algorithm in it to be able to identify each specific piece. The same thing with the snow leopards on the side of the mountain. We give it one, it begins to flatten it out and process it and become more specific and more refined to be able to identify those things. So we need to be able to do those. And the other thing that we'll lead into next is feature engineering. So if an object or something we're looking at doesn't necessarily have the feature needed for an ML or deep learning model, right, then we have to transform it. And the easiest way to kind of understand that would be, I'm going to take to and from IP address and to and from ports in the protocol. I'll take those and I'll create an MD5 hash of that, and that will be used as my new feature to compare things or find nodes or identify something in the space, right? Data labeling. Cloud architecting, it's on here, but I'll say resource architecting, most likely. Who loves the cloud? Who likes on-prem? Man, you guys need some Red Bull or something today, right? Long day, right? None of you like on-prem or cloud stuff? Well, on-prem? All right, thanks for playing. On-prem is the right answer. Sometimes. Right? So identifying where you're going to store that information, where your data is going to be out, where your models are going to run, right? That's really important. And then when we get into some of the use cases and some of the tools and everything else, you'll see that there's an argument for both, right? There should never be a thing where I'm only ever going to use cloud or I'm only ever going to use on-prem resources, right? I'm going to show you why it's important to have a mixture of those environments and a mixture of those capabilities to be able to do what we're going to do, right, as we start pushing further out. Then we actually get into the nitty-gritty. And we haven't even really talked about doing anything data science-y until this point when we start looking at, we're going to train the models, right? Everything else has been preparation to do data science with it, to run the machine learning, to run the deep learning, to generate the AI, right? At this point, that's when we get into fitting the data, right? Fitting the models to the data set to be able to train it, to be able to identify the information as we go through it, right? And when I say fitting a model, we have to take and look at a data set, and let's just say we want to identify people. We need to be able to train that model to be able to identify people in the room. We need to first take a subset of the people in the room, right, and feed it into the model and be like, hey, we're gonna change some of these individuals around, basically, and train it in, and then we're going to take test data, and we're going to run the model against it, and we're going to get confidence levels out of it. We're going to see how accurate it is, right, based off of that. Now, in some algorithms and some data sets, that piece will take longer, right? If we're looking at high precision information, you want to be able to have a very large amount of data, right, to be able to train your model against, to be able to continue to reinforce that algorithm, to be able to then more precisely identify the things you want, right? And if it's something you have a lot of data on, then there's other techniques to be able to fake the data, you could say, or provide notional data into the model to be able to say, okay, I have a high confidence now that if it does see this in the wild, that it is going to perform right. I'm going to pause here really quick and talk about something, though, with AI and training and fitting models and that piece. When we get ready to do these things, we have to kind of think about one very important thing, and that's the criticality of the decision-making that the AI is going to perform or the machine learning is going to perform, right? Do you want high confidence and really extremely resource-intensive AI to be able to give you recommendations about Netflix movies? Maybe, right, if you're concerned with things. Do you want low-confidence models trained on limited data sets for autonomous vehicles? Probably not, right? You want that to be precise. So in that discussion, when you get ready to go through, that needs to be one of the things that is discussed is what's the criticality, what's the cost to human life or the impact on humans, right, or impact on resources someplace, the destruction of equipment or whatever it might be. What's the criticality of this going to be? And that will set the follow-on portions, like identifying the appropriate sample size of your data, of the data that it potentially could see, so that you can make those determinations, right? And there's another subject on sample sizes versus population sizes to drive testing and training of models and everything else. That's like another, I guess, a whole series of talks that you could potentially say. But once you have that, right, you can then drive into the next piece. And if you think about some of the pieces we're going to talk about later on and everything else, right? Anybody got a Tesla? One or two? Everybody got the self-driving mode yet? You use it all the time? Not all the time? That might be even more dangerous. No. Yeah, don't even trust automotive. Well, think about this. When the car comes to you, is it trained for your area? It's not trained for your city, right? It knows a very limited set of instructions that the AI knows how to do. But over time, it can take information in and start learning those pieces. As we move more and more in the direction of having autonomous vehicles, we're going to have to apply things like computing at the edge. Everybody's heard that buzz term, right? Compute at the edge, resource at the edge. So one of the things autonomous vehicle producers are looking at is taking edge compute resources and putting them in places like neighborhoods, renting out attic space, paying for power to them, cooling to them, and everything else. And as vehicles move into the area, they're going to offload data to the edge devices. The edge devices then will retrain their models they have for autonomous driving vehicles, move that data back up the road, and offload it to vehicles moving into the area so that it can continuously learn and add algorithms. And your car and all the other cars will be continuously retraining models, transferring models, and going through. And that's probably one of the best examples I can give you on what AI is really trying to do. It's not a one-shot piece. It's got to be a continuously moving portion, right? A continuously moving process of training those models, making sure that your confidence levels are high in it, and getting it back out to whatever it is you're going to operate at, right? Then once you have those, you start driving your predictions. You start being able to let the car drive by itself. Then you're going to go into post-processing, or what we call ML ops, putting it out there, letting it do its job, right? But you're not going to just let it go free-for-all. Then there's a maintenance tail to it. Again, making sure that the data doesn't change. You have data drift, right? Is it continuously getting what it needs to do? Is the data provider not changing anything? Anybody work with data, and the data provider gives you a set of data with features in it, and then you have your analytics running on it, right? And then the next 2 months later, all of a sudden you get the data set, and they've arbitrarily changed the feature. One person, the data scientist in the back, yes. He's going to get a sticker after class. Right. You have to watch those things, right, so that you understand what's going on in your model and making sure that the predictions coming out the other side are also correct. Because as the data drifts, the model's going to drift, right, and then your predictions become not very good. And then you have your operational deployment. And then guess what happens from there? The process starts all over again and goes through, and you have to continuously do it over and over again. And it's also not a linear process. Inside of here, when we're doing each one of these steps, you may run into a surrogate problem with your data, a surrogate hypothesis that you're going to have to go back out and handle, data cleansing issues. You have to get sample sizes, everything else reset. So it might take several iterations of each step to be able to move on to the next one, to be able to get to the final product, of being able to do, right, and run and deploy AI to be able to do these things. Right? Two types of data, right? Structured and unstructured data. Right? Structured data, when we're talking about that, it's things that have labels or feature sets, right, that we know that we apply to it. It usually consists of numbers or some sort of text, date, strings that are always going to be not necessarily exactly the same, but are going to be in a defined table. Right? If you think of it like everybody who loves Excel, number one analyst tool in the world, Excel, right? If you think about structured data, that's the best example I can give you, or CSV. You put You got a column, you give it a label, and you start putting data into it. You want to add another column to it, you give it a label, and you start putting data into it, right? That's structured, right? So when you get ready to analyze it, whether that's you push it over into a pivot table, you can reference those values in the table by its label and position, or you can do some other pieces with it, like feeding it into a data lake someplace. You want to feed it in a data lake, and then grab it out with pandas using Python, right, to be able to understand those pieces. About 20% of enterprise data could be considered structured data, right? We have far more unstructured data than we do structured data. It requires less storage. So if you think about, we take data from someplace and we flatten it into columns and rows, right, of data, we can store a lot more information in a CSV file than we can in any other type of object. If you take it and you put it in a Word document, right, and you store it in an entry or record in 1,000 Word documents, or you take all the information out of it and put it in one CSV file, right, we don't have to manage it. And that's important, too, when you're talking about this pieces, that power, space, and cooling you need to be able to run your resources, run your analytics, and store your data, protect your data, right, and be able to get to it, comes at a cost, right? If you're talking about, how many of you ever had the discussion about whether you're going to pay for on-prem or off-prem storage? Again, the data scientist, right? That's a very valid question, right? How much does it cost, right, to spin up AWS storage and hold it, right? The other thing, too, here is, I don't talk too much about it, but is dark data. You'll get a file, you'll get information in, and you only use 3 or 4 of the values within the data, right? But there's all this other data that you have access to, and data scientists want that data and want to be able to inspect it and use it and see. And you'll hear me talk about atomic values of packets, right? Using not just the top-level labels or feature sets of packet, but being able to look and derive other information from it. It's stored in there. If you don't absolutely need it, then there's no reason to store it, right? If you start looking at expanding your data storage and you're only using 25% of it, but you're paying for 100% of the storage and cooling everything else, you're just wasting money. And you're also wasting storage space and compute resources and everything else to be able to manage it. It's easier to manage and protect because we can lock it in. We can do things like cell-based protections and all those other cool things. Right? Unstructured data can't normally be displayed in a format that is readable in a structured way, right? Now, that's not to say that a Word document is not structured in some way, but it's a group of words, it's a group of strings that we can just dump in someplace. And if we took it out of its format within the Word document, you wouldn't necessarily know how to read that data, right? Images, video, emails, some spreadsheets. How many of you love spreadsheets without column names on them? Right? Nobody loves that. That could be considered unstructured because you really don't know what the features are in that. It's now just a huge jumble of words and cells, or strings and cells, or integers and cells. Right? More difficult to manage because there's no structure to it, right, so on and so forth. Basic machine learning types. In machine learning, we have unsupervised learning and supervised learning. Unsupervised learning is going to do a couple things for us, and it gives us an advantage when we look at the examples here in a few minutes. Right? It's a way to be able to take a structured data set or unstructured data set and feed it into the machine learning algorithms or the deep learning algorithms and letting it decide or detect clustering of objects and features within the table, right, inside the data. So if you put PCAP data in and you're like, just tell me something in there, it will then start grouping and clustering objects, right, rows of data together and say, hey, this object has this feature set, and it looks like it matches this. And you might say, it's clustering on protocols. So you'll have all the DNS clustering, you have all the HTTP clustering, you have all the mail clustering up and everything else. And then you might start seeing outliers that aren't really clustering. And then you, as the cyber person the DCO operator or OCO operator can then go in and say, what are those outliers? I know these other clusters are normal traffic or should be normal traffic. I'm not saying that there's not bad guy activity in there, but you can start seeing other things that just don't fall within those clusters, right? Those outliers to be able to cut down. And think about it in this fashion. If you're looking at 100 PCAPs, you might be able to do that as a human. But if I give you 20 million PCAPs or 20 million objects, you're just not going to be able to do it. Who's going to go through 20 million rows of data in Wireshark? Even with the best filters. Probably still going to miss things, right? And when we start looking at other pieces to data science, we start going from a couple 100,000, a couple million, to trillions of events. How many people know how Twitter works? You send a tweet. How many packets does a tweet generate? A tweet is a single packet. If Kim Kardashian has 100 million followers and she tweets that she hates Kanye West, how many packets are there? There's at least 100 million packets. And for every device that person is logged into, that's another packet. So if we all have 2 or 3 devices, right, it's going to go to those devices. That's a potential 300 million packets of data. And if you're doing analysis of information on Twitter, think about how many people are sending tweets around. And every time one of Kim Kardashian's retweets that, or ats her or anything else, that's another deluge of those pieces. So if you're looking at using Twitter for sentiment analysis, cyber threat activity for specific regions, you could be looking at literally trillions of emails or trillions of tweets. So using it to be able to get through those things and be able to cluster pieces to be able to at least go an initial triage is very important. Right? Supervised learning. And there is semi-supervised learning as well, but we're going to focus on supervised learning. It's where we take that data and we say, I know what features I want it to learn. I'm going to go in, I'm going to pull it down, I'm going to apply the models to it and kind of hone it in so I can tell it what I want it to cluster on. If I have that PCAP data, I can then say, hey, I want you to take the to and from IP address and the protocol or some other feature and say, this is what I want you to now identify other objects with and train it. And I say, this is bad, right? So it's going to go through and it's going to cluster all the bad objects inside the data set together and be able to go forth or create some other level. Right? There's classification and there's regression, and we won't get too deep into that piece. Now that I've completely bored you with the AI talk, we're going to get in how we can apply this in cyber. Right? How do you begin to use some of these pieces and pull it into the cyber universe, right, for DCO or for even OCO operations, right? And the first is going to be anomaly detection. Everybody loves anomaly detection, right? So what we're already trying to do, who uses Snort? I can't date myself that bad, right? Nobody's using Snort anymore? Anybody using any type of alert, like an IPS, an IDS, or one person? So what we do is we're looking for alerts to be able to find anomalies within the traffic, right? Well, if I write an alert or I write a rule to be able to identify that anomaly, I'm inducing some sort of bias. I might miss it. But I can use anomaly detection to be able to go out and say, I want you to look at all the data that I have and be able to then start clustering those pieces up and classifying them to be able to identify in some sort of network map, right, a neural network almost, of objects that are going on. And it's not just at a single object layer either. We can take things like network traffic and net flow information and model human beings on a network and put all those in the same thing, in the same model, so a model of models, and run those simultaneously to then create pieces and not just baseline a network, but baseline the entire environment that we're looking at of everything that might be going on inside there. So then it knows what's going on. It might be able to, an individual might be able to fake an alert rule to make itself look like a machine. But with these, as they continue to learn, right, as these models continue to learn, we can then find nuances and let the machine see things and changes and anomalies in that traffic, in that environment, to be able to then float it to the top and alert us to what's going on. Again, it's beyond just baselining the network traffic, right? It's looking at everything that's going on inside of there. We have real-time multi-model detections systems and distributed networks. That's a lot of buzzwords in one little bullet, right? Multi-model distributed architecture, right? So I will tell you also, I'm a fanboy of NVIDIA. Anybody like NVIDIA? Everybody loves NVIDIA. Everybody, if you don't know, right, it's not just a gaming, or it's not just a video card company. They're driving AI right now. If you go out on the floor and you're looking at companies, I bet you they've got some sort of GPU-based AI processing, and it's most likely going to be NVIDIA-based, right? A DGX A100 or an A100 card or some other GPU-based piece in there. So with them, we can take pieces like their Morpheus framework, and I would suggest if you haven't ever seen Morpheus or heard about Morpheus, go to NVIDIA's website and look at Morpheus framework. It's their cybersecurity architecture they're building to enable us to use the GPUs for anomaly detection, right, in these environments. And what I was just saying a second ago was it's now building on a map, and this is an example of Morpheus running. We're able to take multiple modes or models and be able to say, this model here identifies humans on the network, and this is my insider threat model. And this model here is what I'm going to identify all my normal network traffic for hosts, and this is what's going to be my backbone communications model, right? And they're all running simultaneously. It can scale, right? Depending on your architecture, it can move across and scale out and be able to process more and more data, right? And then find those things. We train it. Like I have a model like this running where we train it over a 72-hour time period and can get a baseline of the network and then be able to identify the anomalies and everything else and throw alerts to you. Now, try to do that with a SIEM that's running an IDS, right? You have an IDS that's running. You may not be able to detect like humans pulling things off that don't trip the IDS, right? Doing things that they normally wouldn't do. Being able to identify things like working outside of the scope of their privileges or working out of the scope of their normal time frames that they're supposed to be at work, right? That wouldn't necessarily trip an alert for something, but a little nuances in that can be used. Right? Natural language processing. Right? This is another big one for phishing detection. And it's not just normal phishing detection works on very basic phishing detection. It works on inspecting the URLs or domains within the email and making sure that what it's saying, presenting to the human, and what's really in the underlying code in the email match, right? Or that it's not on some other list someplace else. With natural language processing, right, we're taking the entire email, right, the raw email itself, right, or both the URL and other underlying information within the session and the raw email, and being able to create these deep neural networks to identify some sort of nefarious activity, being able to detect changes in the way a person speaks. Who has never gotten a Nigerian email scam? None of you? You guys are like the luckiest group ever. You've never gotten it? You know that the English in those things are pretty horrible. Even when they get really, really pro-level Nigerian print scams, right, it's still, you can detect the non-English. Or you can detect, right, if you're looking at Twitter for misinformation campaigns, you can detect and see that sometimes that English or some sentiment inside of there doesn't match up to what they're actually portraying to the end user to trying to get you to click on something, right? So we can build those pieces out and over time identify the nuances in the language being used, and that to be like, hey, the link in this is correct. It matches what's being presented to the user. I don't have it on a banned list somewhere, but the language inside the email just doesn't match what a human would say in this instance, right? And it can be used against other language sets as well, right? So we're not just looking at like English language. We can apply that to other languages in the world, right? And we're able to use those GPU processing to be able to do that type of stuff, to teach it what those things are, right? Using sentiment analysis and other aspects of it. Right, so it just gets us deeper in and more advanced. Adversarial artificial intelligence detection and defeat. Now, this is a big topic that you'll probably hear it like on the periphery of the AI discussions, especially within cyber. Right? But it's a big one that we discuss all the time in my lab and with partners that we're working with. And that's not just applying AI in offensive or defensive operations, but it's how do we, protect those models? How do we defeat models? Guess who's using machine learning, AI, and deep learning? Our adversaries use it. And they use it faster than we're using it right now. Right? They're not constrained by some of the same issues that we have, some of the same legalities that we have, some of the same misunderstandings or resource constraints that we have, right? But they're using it. They're also using it to see how they can defeat as we ramp up our use of AI, especially in the cyber sector, as we ramp it up to be able to protect our networks, to be able to defend the things we want to be able to defend. They're looking at ways of how to defeat it, right? So they're taking the same capabilities, same anomaly detection engines, and they're first running scenarios where they're trying to defeat those algorithms, and then being able to turn it back on us and our networks and against our AI and seeing if it can be defeated. And it's not just on network traffic, it's on a lot of different things. Like adversarial AI could be considered deep faking. Right? Everybody familiar with deep faking? Right? So being able to take a video of somebody else and produce a new video where it's not them talking or not them giving some order. Voice deep faking, so you fake your boss's, well, I wouldn't say you fake, but the adversary fakes, right? Your boss's voice on a phone call and tells you to send the check to somebody else, right? So they're using these things to go in there. So you have to look at when we're applying, right, or developing out machine learning algorithms or developing out and storing or executing and operationalizing AI, how are we protecting it? How do we protect our data, right, so they can't get to the data or inject into the data and cause data drift purposefully, right, and maliciously in that fashion to be able to then defeat the algorithm or cause us to lose faith in what our models are telling us, right, the output of the intelligence coming from those models, right? If I'm continuously throwing a false alarm, what would you as an operator do? You're just going to hit the button and say, that's fake. That's fake. And be done with it, right? So we have to watch those things and be able to protect it, right? We have to watch our compute resources. I know that one of the biggest targets out there right now is trying to get on any of these systems, right, that's running any of these algorithms or doing anything. Deep learning pods out there, any type of resource that's running, right, artificial intelligence, getting on and watching and seeing what algorithms are being run, how are they being trained, how are they being tuned, right, so that I can then go back and see and understand, right, how I need to affect those or how the adversaries are going to affect them, right. And in this case too, this is where we're also looking at, augmenting DCO operators or augmenting OCO operators, right, or augmenting even Intel analysts, right, and not replacing them. Because it's still going to take a human, everybody's heard the buzz term, human in the loop, right? It still takes a human to be able to make that determination. The more critical something becomes, the more important it is to have an actual human sitting with the AI, machine learning, or deep learning, and making sure that it's doing what we expect it to do. Even in full auto, driving autonomous vehicles, it still wants you to be awake, right? It still wants you to be able to, at a second's notice, be able to take control of the vehicle and do something, right? If it can't stop. Who's got lane assist in their cars? A lot of people, right? It's a form of AI. It's looking at lines in the road, and if you take pressure off the wheel, it's going to vibrate or it's going to alert, it's going to do something, right? That's because it's not fully implementing full auto driving, it still needs you to make corrections for it if it's going to drift outside of its normal piece. Same thing here. It still needs us to be able to look at those things and make determinations if it is. It's helping us. It's clearing away all the other things that we have to do, the alert fatigue, right? We can get more precise in those pieces. Tools of the trade, right? If you look across the ecosystem right now, and in the past, let's say 10 years when we've been talking about big data analytics, and now we're getting into machine learning and deep learning and AI and everything else, some of the tools are somewhat the same, right? Now, anybody use Jupyter? A couple people, right? So we use Jupyter. We're now taking Jupyter and Jupyter Labs and putting on compute resources that are GPU enabled and getting faster processing, right? Where it would normally take, if you run a GPU or if you run Jupyter on your notebook, right, and you're processing PCAP data to be able to derive some sort of intel from your algorithm, right, it might take you 45 seconds to run 100,000 rows or 100,000 packet, right, samples through it to be able to derive some information. Now with the Rapids AI and enabling the GPUs on it, we can take that 100,000 rows and process that in 4 milliseconds. And it scales out. So if I have 100 million or I have 100,000 rows and it takes me 4 milliseconds, now I can take terabytes of data, run it through the GPU, and I'm not looking at days of processing, I'm looking at seconds of processing. Right? And I can now start moving things into place, and we'll talk about it a little bit more in a second in the hardware. I can start doing things that I really want to do, and it's not taking me a long time. In the earlier days, before we started doing GPU accelerated processing for AI and machine learning and deep learning, there would be times where we'd try to train a model, and it would literally take days to train the model. Now with higher-end hardware, enterprise-grade hardware, it can literally take a few minutes to a couple hours to be able to train that model. And where that really becomes important is when we start deploying these types of things out to the edge, and we're looking at vast amounts of data. Like we can move not just from like our network taps, but we can move into like enterprise taps or even like national level taps and be able to process that data, take it off, retrain the model, and then redeploy it back on in a timely manner. And it's not taking days, weeks, or months to be able to do that, right? We're talking about seconds and minutes and maybe a couple hours to be able to do it. TensorFlow, Docker and Kubernetes, right? Some people might say, well, why do you have Dockers or Kubernetes on an AI discussion? When we're developing these models out and we're training them, we need to operationalize them on that data science process, right? When we get ready and we've trained the model and we've got our predictions running, then we have to deploy it. We can take and we're deploying these things in K8s and Docker containers, right? So that we can scale out across things. Morpheus works really well because it can then sense increased network traffic or increased data production and start scaling out. And it's just spinning up instances of Docker containers or Kubernetes and being able to say, okay, I can now handle the full capacity and stay right in time with it and still provide near real-time alerts. Right? Machine learning enabled teams. Who uses Splunk or Elk? Splunk or Elk. Right? They have some basic ML capabilities in it. I love Elastic, but I will say that their capabilities inside of their services are very limited, right? There are ways we can do other things outside of Elk that would be really beneficial if we could do it in Elk or be able to do outside of Elk and feed it back in. And there's ways to kind of do it and fake it, but those services inside of there are very limited in what they can do for you, right? So you have to come out of the scene, right, and then go and do actual data science-y type stuff on other infrastructure and then produce the data and maybe put it back into Elastic and then have your dashboards and everything else set up for you, right, for visualizations. Or generate your own visualizations and just not even use Kibana, right, do something else. Now, hardware. Again, I told you I'm a fanboy of NVIDIA. They have incredible GPUs. They're being used all over the world. They have a lot of really cool stuff. And kind of the architecture or the framework for what we're looking at and being able to do these things, it's going to be CPU, GPU, and DPU. Everybody knows what a CPU is. We know how it works, basically, right? Inputs, outputs. It's really good at doing some things and not really good at doing others. Data science on large data sets, I say extremely large data sets, is not really effective with CPUs, right? They can get you to a certain point, but then you're going to start seeing bottlenecks and IOs to be able to do the things you need to do. That's where GPUs come into play. Being able to use its throughput on its IOs, on its chipsets, to move vast amounts of information back and forth really quickly to be able to do those things. And even on the backside, on the networks of the GPU systems, we're looking at being able to do things. Anybody ever hear of a company called Mellanox? So Mellanox switches have a protocol called InfiniBand, where we can actually take enterprise-grade GPU systems, connect them into this InfiniBand, divide up the GPUs on two different systems and cluster them together and have near zero latency in the processing of those pieces, moving information across the network to the GPUs to be able to do those, right? One of the things you'll start hearing about a lot coming up as well as DPUs, right? And that's where we're taking the processing off of the GPU and taking GPU-like processing and putting it on a smart NIC card. So we can take all the machine learning and all the AI and all the deep learning algorithms and put on that card, and now we have access to all the telemetry data that's on the card, all the data that's running across it in near real time. And I think my NVIDIA rep yesterday was saying that they were working at 480 gigs per second, being able to, with zero loss of data and being able to hit everything and do real-time alerting on some of the initial NVIDIA tests. I will caveat that they're testing on their systems, right? So what we actually get in a while may not be the same. But the other thing, and this is a really good reason why I like NVIDIA GPUs, is because the code doesn't change. If I'm doing the code, or if I'm accessing and I'm writing in Rapids, right, which is CUDA environment, CUDA code, I have access to those same processes on GPUs. And if I want to move my code to the DPU, I just move it to the DPU, and it starts working. So I don't have to change my code processes, maybe slight tweaks and versioning of things, but I'm not having to rewrite things constantly. And where that really comes into play at is when we throw in the cloud architecture on top of that, and we push to the edge, right? Everybody knows that DoD has a huge data problem, especially in cyber, right? Like we have the BDP, we're putting all the services have their own BDPs and have their own services, and it's all over the place. And what's the first thing analysts tell us, whether it's cyber or intel analysts, like, I just want all the data brought back someplace. I want all the data. What we really should be doing now as analysts and cyber folks is being like, I want to push my algorithms and my processing to the edge. I want to get as far forward, right, so I can start doing real-time detection and anomaly detection in this environment. And where it comes into play at is you don't have to rewrite code to do that. You can go from a desktop, and NVIDIA, again, has nano development boards and NX development boards that are $100, right, or $400. I can do the same code set on those devices, and then when I get to the point and it's trained properly, I can move it to a $500,000 GPU. Or I can move it out to a DPU on the edge, and it all will work together. And as I'm doing anomaly detection, if I was doing Morpheus, if I'm doing anomaly detection and I train a model in a geographically different area, I can take now and pull that model back and deploy it back out in almost real time, inject it back in, and start doing my detection. So all of them now become self-aware in almost real time to be able to do anomaly detection. And I say self-aware not as in a sentient artificial intelligence, but aware now that it's been trained from other data across the place, which then makes what? The model stronger, more accurate, more resilient, right? We can do these different types of things inside there. So you will need to look at all four of those at some point in your processing, your resource designs, and everything else, right? Can I do it on CPU? Maybe, right? Depending on the amount of data and amount of processing. Do I need to do it on cloud? It might be a time for you to have to do it on cloud and move it up. It might make more sense to do it there. Or on-prem, right? The way of the cyber warrior. I know we're getting close on time here, so. What do we need to do for operators? What do we need to do for anybody in this room that wants to learn AI and become more skilled in this area, right? We're looking at multi-discipline domain folks and experts. And when I say that, I'm talking about, you might be a computer science guy, you might be a mathematician, you might be a cyber operator, a DCO operator, OCO operator, you might be a SOC, right, analyst, right? We need you, right, and we need as a community to start picking up some of these skills and at least start being able to discuss in detail and understanding what we're discussing today, right? And being able to go back to our colleagues and our bosses and our leadership and to be like, hey, I know you said AI, but do you really know what AI is? Right? And have those pieces in there. And we can start picking up some of those pieces so we can help guide the future of AI as we implement it into this environment, right? Some of those things will also dictate the capabilities we provide. Like if you come over and see our kit tonight at the Cyber Center, one of the things we did was we realized that junior military folks coming out of A school or your initial training, right, are not going to have data science skills. So we as developers want to give you not an easy button, but drop downs. Like I want data from this location, and I want to be able to process it through this model, and I want it to be output to this location and in this format, right? To be able to go through, and as you build up your domain expertise, and this is assisting you to get to employing ML to help augment your capabilities, you'll be able to start understanding more deeply how it's working, being able to now affect the training of the models, being able to say, yes, this is working, the capabilities are working for us, and it just makes you and makes your coworkers just better all-around operators, right? We kind of joke around about anybody who's DCO, OCO, and a data scientist is really a unicorn, right? It's hard to find DCO operators, right? It's hard to find OCO operators. It's hard to find SOC operators that don't want to go and work at a gas station after 6 months of watching alerts go off, right, on their SIEM all day long. But this is what we kind of need to get to. Not necessarily that you're going to be an extreme expert in any one of these areas or all of these areas altogether, but we have to be able to start building up the skill sets to be able to break out of it. And I joke around quite a bit with people ask me, and I'm like, what's the number one thing I like to do? And that's break SOC operators' bad SIEM habits, right? And that's because they get sucked into watching the dashboard, right? Instead of asking the question of what's in my data, what's in the environment that I'm missing because it's being presented to me. And maybe Bob made that dashboard, and Bob didn't know how to write the query correctly to get the information out of there. Or he didn't consider, well, what if I take this data from this location and this data from there and put it in the same data set and create some new object that now really identifies what I'm looking for, right? So breaking out of the SIEM-focused defensive cyber pieces. Cyber data, right? As we move into 5G, it becomes more complicated. Who was in my talk this morning when we were talking about critical infrastructure? A couple of you. Imagine the amount of data that we're talking about in critical infrastructure, right? Buildings this size producing vast amounts of data just from their systems that use to operate it, right? To turn the lights on, to run the HVAC, to communications, anything and everything inside of here, now producing some sort of data. How fast is it coming, right? With a variety of those types of data, adjacent, critical infrastructure adjacent to my enterprise infrastructure, right? And how we can cross-pollinate or cross-analyze that data sets to be able to get to the things we want to get to, right? Looking at the atomic composition of data, right? And getting away from just, common schemas, but expanding on the common schemas. Like I have 10 features of a data set, but I really know that if I take these other 3 things inside of there and I extract those and now add it to it, now I've got an even more refined object that now I can use as differentiators as we're doing clustering or classifications, right? So generating your own information, being able to pull those pieces out there. Making sure that when we do that it's common across platforms, right? They try to do that in the BDPs and in other data sources and everything else. But I guarantee you if you go to any data lake, right, you're probably going to find data that looks the same, but somebody's mislabeled it, right? or whoever generated it has gotten it wrong, right? Or just didn't know, or it's human error and they misspelled it when they labeled it. Right? I've seen it happen before. So being able to do those things, being able to expose that out and across the communities, to be able to pull things across, right? And like I said a minute ago, edge compute is going to be the future, right? Moving these capabilities out to the edge as far away from us as we possibly can to get deeper and deeper into the data sets, to get deeper into the net flows and the network information and into the wild, so we can start doing anomaly detection really at scale and as fast as we possibly can is going to be very important. Yeah. So, in conclusion, before we get everybody out of here, right? We've got to adopt and understand AI at the speed of innovation, right? We can't be afraid of it. And we got to go back to our bosses and our resource providers and everything else and be like, hey, we need this, but this is what we need, right? We don't need to just go buy a bunch of AI stuff off the shelf, right? We need to be able to do it in a meaningful manner, but we need to start accelerating how we adopt these pieces in it, because our adversaries are adopting them just as fast, if not faster, and moving ahead of us and getting further out in front. Ever-changing cyber environment, right? It's going to require us to be agile, be able to use things, use common schemas, common language sets and capabilities. And if my strategic officer for my company was here, she would love this, the art of the possible, right? It's allowing you as operators, as analysts, as network operators, whatever you might be, to be able to go, you know what? I want to look at something and I want to find something different. I want to make sure something's working properly, and I can stop looking at, again, just at SIEM and the normal data and really expand out and start grabbing other pieces so that you can really, really dive into what you want to find and what you want to train and what you want to be able to bubble to the top on your operations. I appreciate you guys coming out. Does anybody have any questions, discussions? Right here. Well, so if you get like Jupyter Labs and you can start looking at some of the other models and some of the other data science algorithms that are out there, and it's not to disparage Elk or anything else. It's an awesome product and everything else, and having the machine learning in there. But there's limited ways that you can then affect and retrain the models or change the algorithms they've already put inside of there. Like we've talked to them about, hey, you know what, just drop those models and allow us to get out into something else to be able to pull information and run other algorithms or other data science models or deep learning models to be able to identify the things we want to do within Elk or within Splunk or whatever object it might be, or the application. Any other questions? All right, I appreciate it. Guys, don't forget to scan your badges and get credits. And a shameless plug, everybody know where the GCC is at? If you go up to the 3rd floor of the clubhouse, we got beer and bites tonight. Come by. We got some really cool AI stuff going on over there. You'll see another company and some CTF platforms and everything else. So come on over and get a beer, something to eat.